Okay, so in this video, we're going to be talking about determining limiting reagents. Okay, determining limiting reagents. Now, we need to ask ourselves a question to say, what is a limiting reagent? Okay, what is a limiting reagent? Now, to establish this, we must first understand that the terms reagents and reactants can be used interchangeably. So if someone says limiting reagent, another one says limiting reactant, they're just talking about one and the same thing. Okay? So limiting reagent, limiting reactant, that's just one and the same thing. Now, by definition, a limiting reagent or a limiting reactant is any substance that is completely used up during a chemical reaction. A substance that is completely used up during a chemical reaction. The keyword there is completely used up, okay, during a chemical reaction. So, if a substance is not completely used up during a chemical reaction, we cannot term it as a limiting reactant. However, we're going to term it as an excess reactant. So, a limiting reactant is completely used up during a chemical reaction, while an excess reactant is not completely used up during a chemical reaction. Anytime you're handling problems like these, everything should be done with respect to the limiting reagent or with respect to the limiting reactant. Why? Because the limiting reactant here determines the periods of the reaction. It's the one that actually determines the duration of the reaction. If the reaction is going to take 3 minutes, 5 minutes, 7 minutes, what is going to be determining that is the limiting reagent, is the limiting reactant. Okay, it's the one that actually determines the period or duration of the reaction. Now, when you are determining the limiting reagent, there are two methods which I can introduce to you. We can use the mole method, or we can introduce or use the mass method. Okay, so the mole method or the mass method can be used in determining your limiting reagent. So in this problem, I'm just going to use one method, however, and I'm going to use the mole method in determining the limiting reagent. In some other videos, definitely I'm going to also explain how the mass method can be incorporated in determining the limiting reagent. Okay, so let's get down with this. So in this question, they're saying that in an experiment to prepare a salt, a learner reacted 3 grams of magnesium oxide with 40 centimeters cubed of dilute nitric acid of concentration 2 mole per decimeter cubed. And then the question is just so direct. They're like determining the limiting reagent for this reaction. Okay, determining the limiting reagent for this reaction. Now, anytime you're trying to determine the limiting reagent, it's very much important that you write a balanced chemical equation for that reaction. If you don't write a balanced chemical equation for that reaction, you are going to be finding some challenges in determining your limiting reagents. So the first thing that we're going to do here is that we're going to write a balanced chemical equation for this reaction. What are the reactants given? We are seeing that there is magnesium oxide and there is also dilute nitric acid. If you are to write a balanced chemical equation, it's important that you also learn how to write correct chemical formulas. So how can we write the correct chemical formula for magnesium oxide? Well, magnesium is in group 2, so it has a valency of 2. Oxygen, or the oxide here as well, also has a valency of 2. Now, when you see that two given elements, like the magnesium and the oxygen, are having the same valencies or equal valencies, what we normally do is that we just write them directly together. That is, you're just going to write them as magnesium and the oxygen just brought together there. Or if you want, you can interchange them. Mg2, the 2 is going to come with the magnesium. the oxygen is also going to have a 2 down there. But normally we just don't write it in this way. We try by all means to write it in its simplest way. And we're going to see that the numbers that we're having down here are 2 and 2. They're the same, and they are exactly divisible by 2 itself. So this is the whole reason why it's just going to be brought back in that way as magnesium oxide. That is just writing the magnesium and the oxygen directly. So what we're going to do here is that we're going to write magnesium oxide as we have just seen. Magnesium oxide plus, and then we're seeing that this thing is being reacted with dilute nitric acid. For now, we are going to overlook that term dilute, but there is a distinction between dilute nitric acid and concentrated nitric acid. There is a distinction right there. Now, the question is that what is going to be produced? This reaction is a neutralization reaction. Magnesium oxide is termed as a basic oxide. In other words, it's a base. Just by the term or the name given, dilute nitric acid, this is definitely an acid in nature. So when the magnesium oxide reacts with the nitric acid, when a base reacts with an acid, the compounds or the substances which are produced are always a salt and water. So what is going to happen is that the kind of salt that is going to be produced in this problem is that the magnesium is going to directly combine with the nitrate. The magnesium is going to displace the hydrogen. So what we're going to have is magnesium nitrate and water. Water is always a byproduct of this reaction. So the question again that we're going to start asking ourselves is that how can we write magnesium nitrate? Well, magnesium, as seen above, has a valency of 2. The nitrate is nitrogen combined with 3 oxygen atoms. And the nitrate, however, has a valency of 1. So if we interchange these numbers like we did briefly here, what you're going to have is that this is going to be magnesium, the 1 is going to be there. You're going to open your brackets, you're going to write your nitrate, and then you're going to put that 2 just outside here. Okay, but of course in most cases we don't show the 1, so this is just better writing as magnesium without showing the 1 and then nitrate in this way. Okay, so this is how your magnesium nitrate is going to be looking like. So magnesium nitrate is going to be written in this way, and then you're going to put your 2 just outside there. And then, of course, what we're also going to yield or produce here is H2O, water. Is the equation balanced? That's the question that we're going to start asking ourselves. Is it balanced? Let us check. There is one single nitrate here, if we look at it. There are 2 nitrates present here. There are 2 hydrogens. There is 1 hydrogen. So the best way in which we can balance this thing up is by just introducing a 2 as the coefficient there. Because this 2 is not only just going to be working for the hydrogen, no, it's also going to be working for the nitrate. So 2 hydrogens are seen, 2 nitrates, 2 nitrates, which are available or which are present there as well. Altogether, magnesium, just 1. Let us look at the oxygen atoms individually. There are about 7 oxygen atoms. 2 multiplied by 3, 6. So there's 6 oxygen atoms here, plus that 1, 7. 6 oxygen atoms here, plus that 1, 7. So that's it. The equation is now balanced. Okay, the equation is now balanced. Now, once you balance up your equation, what we now begin to do is that we begin to determine the number of moles of the reactants. Okay, we begin to determine the number of moles of the reactants. So in this problem, what we're going to do is that we're going to determine the number of moles of magnesium oxide, and then afterwards we're also going to determine the number of moles of the nitric acid that we have here. So let's see how we can determine the number of moles of magnesium oxide. So let us see how we can find the moles of magnesium oxide. Now, it's important that we see what has been given on the magnesium oxide. Now, magnesium oxide, the only thing that has been given is the mass, which in this case is 3 grams. That's the only thing that has been given. So how can we use the mass to determine the number of moles of magnesium oxide? Well, there is a formula which is given by N, which is the number of moles, equal to mass over molar mass. Mass over molar mass. Okay? Now, the mass of the magnesium that has been given here is 3 grams. But we don't know the molar mass of magnesium oxide, so that's the first thing that we need to do. We need to determine the molar mass of magnesium oxide. So how can we do that? Well, it's important that we try to see how magnesium and oxygen look like on your periodic table. Well, if we round off the values to the nearest whole number, you're going to find out that the mass of magnesium is 24. The relative atomic mass of oxygen here is going to be 16. So magnesium has a relative atomic mass or a molar mass of 24, and oxygen has a molar mass of 16. So having seen that this is 24 and this is 16, what we're just going to do is that we're just going to directly add these values. Because again, we're seeing that there is only one magnesium and one oxygen. So it's just going to be a direct addition between the two, that is 24 plus 16. And 24 plus 16, the value is just going to be 40. Okay, 40. So the molar mass of magnesium oxide is just going to be 40 grams per mole. Okay, so this is going to be 40 grams per mole. Okay, so 40 grams per mole, that's how it's going to be. So let us try to work it out. Let's see how it's going to be. So 3 grams divided by 40, this is going to be 0.075. So this is going to be 0.075 moles. Once you determine the number of moles of magnesium oxide, what you're now going to do is that you're now going to proceed to determine the number of moles of the nitric acid, which is HNO3. There. So notice how is it that in nitric acid here, what we have just been given is the concentration, which is in mole per decimeter cubed, and the volume. These are the only two things that we have been given. We haven't been given the mass, but we have only been given the concentration, which is 2 mole per decimeter cubed. 2 mole. Let me just write it like this. Per decimeter cubed. And the volume value, which is 40 centimeters cubed. So the volume is 40 centimeter cubed. Now it's imperative, very important that you know these formulas. So the first one was number of moles is equal to mass over molar mass. The other formula that I'm going to introduce here is going to be concentration. Concentration is equal to the number of moles over the volume. There is a restriction though. Your volume is supposed to be in decimeters cubed. Okay, your volume is supposed to be in decimeters cubed. What have we here? 40 centimeters cubed. What do we have here? Decimeters cubed, which means that there is going to be some conversions which we are going to start making at this particular stage. Okay, there are going to be some conversions which we're going to be making at this particular stage. So one thing that you need to know is that 1 decimeter cubed is always equivalent to 1000 centimeters cubed. Decimeter cubed can also be termed as 1 liter. 1 decimeter cubed, 1 liter. Centimeters cubic can be termed as 1 milliliter. So someone who says 1 decimeter cubed, 1000 centimeter cubed, or another just comes and says 1 liter, 1000 milliliters, they're just talking about one and the same thing here. Okay, so what we're going to do is that in order for us to convert this 40 centimeters cubed into decimeters cubed, it's just basically dividing 40 by 1000. Okay, just basically dividing 40 by 1000, and when 40 is divided by 1000, our value is going to be 0.04. Okay, 0.04. So if the 40 centimeter cubed has been converted into decimeter cubed, 0.04 decimeters cubed. That's how it's going to be. So after that, we're just going to substitute our values here. Or if you want, you can make the number of moles the subject of the formula. How is it that this is going to be moles, or N if you want, will be equal to CV, where C is your concentration, which is 2 mole per decimeter cubed. 2 mole per decimeter cubed. This is being multiplied by your volume now, which is 0.04 decimeter cubed. You know, conversions are very important because the decimeter cubed and the decimeter cubed here are going to cancel, which is just going to leave us with the mole unit there. So 2 multiplied by 0.04, this is going to be 0.08. So we're having 0.08 moles now. Of the nitric acid. Okay? 0.08 moles of the nitric acid, sorry about that. 0.08 moles of the nitric acid. Here we are having 0.075 moles of the magnesium oxide. So once we do that, we choose any product of our choice, either magnesium nitrate or the water. We pick any product of our choice here. Okay, any product of our choice. And then once we pick any product of our choice, like maybe for instance in this case I'm going to pick magnesium nitrate. Once we pick magnesium nitrate, we are going to use the same number of moles of magnesium oxide to produce the number of moles of magnesium nitrate. And then we are also going to repeat the same procedure, this time using the number of moles of nitric acid to find the number of moles of magnesium nitrate. The value that is going to give us, the value that is going to be high here is the one that we are going to use in determining our limiting reagent. Take for instance, if magnesium oxide produces a higher number of moles of magnesium nitrate, then magnesium oxide is going to be the excess reactant. If magnesium oxide is the one that is producing the least number of moles of magnesium nitrate, then it's the one that is going to be the limiting reagent. The same thing also applies to the nitric acid here. If nitric acid is the one that is going to produce the least number of moles of magnesium nitrate, then nitric acid is the limiting reagent. If the nitric acid is the one that is going to produce the highest number of moles of magnesium nitrate, then it is the excess reactant. Okay, so how are we now going to use the number of moles. How are we going to use the magnesium oxide and the nitric acid in determining the number of moles of magnesium nitrate? Well, the mole method is very, very easy. So what you're now going to do here is that we are going to start establishing something which I like to call the mole ratios. Okay, we're going to start determining what we're calling as the mole ratio. How? If you look at magnesium oxide here has a coefficient of 1, even though it hasn't been shown. So 1 mole of magnesium oxide was being reacted. If you look at the magnesium nitrate has a valency, or rather has a coefficient of 1, which means that we are going to write it like this. That's it. That's how you write your mole ratio. In that way, 1 mole of magnesium oxide was producing 1 mole of magnesium nitrate. Now, once we establish the mole ratio between the magnesium oxide and the magnesium nitrate, we need to interpret this thing very well. If the mole ratio is 1 mole to 1 mole here, I forgot to write the word mole, but it's fine. If the mole ratio is in a 1-to-1 format, then it means that the number of moles of magnesium oxide and the number of moles of magnesium nitrate are the same. Take note, if the mole ratios are the same, that is 1-to-1, then it means that the number of moles of magnesium oxide is equal to the number of moles of magnesium nitrate. That's the thing there. So initially, we had established the number of moles of magnesium oxide to be 0.075, which means that if magnesium oxide is having 0.075 moles, then apparently magnesium nitrate is also going to have 0.75 moles. So therefore, the moles of magnesium nitrate will be equal to 0.075 moles. So 1 mole of magnesium oxide to 1 mole of magnesium nitrate, the number of moles are the same. If the number of moles of magnesium oxide was 0.075 here, then the number of moles of magnesium nitrate as well is also going to be 0.075. So we have only played around with magnesium oxide. What about nitric acid? Let us see how we can use nitric acid now to determine the number of moles of magnesium nitrate. Same procedure, you're going to create your mole ratio. Look at your nitric acid. Nitric acid is having a coefficient of 2. So this is going to be 2. You're going to write your nitric acid here. If we look at our magnesium nitrate is having a coefficient of 1. So 2 moles of nitric acid with 1 mole of magnesium nitrate. How do we interpret this? We interpret this to say that 2 moles of nitric acid was producing 1 mole of magnesium nitrate. 1 mole of magnesium oxide was producing 1 mole of magnesium nitrate. Once we do that, notice that the number of moles of nitric acid that you had determined here was 0.08. So just on the nitric acid side, you're going to put 0.08. And then on this side, you're just going to put X because you don't know what the moles of magnesium nitrate are. It was so direct for this one because it was in a 1-to-1 way. But here it's a different procedure. This is 2 moles of nitric acid, 1 mole of magnesium nitrate. The numbers are imbalanced. So what you can do here is that you can cross multiply, and upon doing so, what you're just going to have in summary is x will be equal to 0.08 times 1. Definitely this is going to be 0.08, and this is just going to be divided by 2. And like we have seen, 0.08 divided by 2, the answer is just going to be 0.04. So 0.04 moles, and then nitric acid. Okay, 0.04 moles of nitric acid. Here, rather not nitric acid, magnesium nitrate. Okay, magnesium nitrate. So here we are having 0.075 moles. Here we are having 0.04 moles of magnesium nitrate. If we compare the two values that we have here, 0.075 moles is greater than 0.04 moles. Okay, so if you took note of what I had said, you're going to see that magnesium nitrate is producing a higher number of moles of magnesium, or rather magnesium oxide is producing a higher number of moles of magnesium nitrate. But if we look at it here, you're going to see that nitric acid is producing the least number, or the fewer number of moles of magnesium nitrate here. So it is therefore at this stage where someone can now make a conclusion to give out which the limiting reactant is going to be. So if we look at it, magnesium oxide here is producing a higher number of moles of magnesium nitrate, 0.075, which means that your magnesium oxide at this stage is the one that is going to be termed as your excess reactant. If we look at it, nitric acid, this reactant of yours, nitric acid, is the one that was producing the least number of moles of magnesium nitrate, which was 0.04. So because it's the one that is producing the fewer number of moles here, then the nitric acid is the one that is going to be termed as your limiting reagent, or your limiting reactant. So that's how it's done. Your nitric acid is the one that is going to be your limiting reactant. So just down here, you can even make a statement to be like, therefore, HNO3 is the limiting reagent. And that's it for this problem. Then you have determined what your limiting reagent is. Just to review, take note. First, write a balanced chemical equation for that reaction. Secondly, determine the number of moles of the reactants individually. This is what we did for magnesium oxide. This is what we did for nitric acid. Two formulas in which you can use to determine the number of moles. Number of moles is equal to mass over molar mass. The other is concentration is equal to moles over volume, where your volume is supposed to be in decimeter cubed. Also knowing this conversion factor, 1 decimeter cubed, 1000 centimeters cubed, 1 liter, 1000 milliliter. Once you do that, use this same number of moles of the magnesium oxide and the nitric acid that you had found to determine the number of moles of magnesium nitrate. The one which is going to give us the least number of moles of the product, like in this case magnesium nitrate, is the one that is going to be termed as your limiting reagent. This is what we started doing. The mole ratio is important. We use the mole ratio between magnesium oxide and magnesium nitrate to find the number of moles of the magnesium nitrate. It was 1:1, implying that the number of moles of magnesium oxide and magnesium nitrate are equal, are the same. The mole ratio, however, between the nitric acid and the magnesium nitrate was 2 to 1. When we evaluated, we saw that the value was 0.04. Magnesium oxide gave us the highest number of moles here, which was 0.075. So that's the excess reactant. Nitric acid gave us the least number of moles of the magnesium nitrate, which was 0.04 moles. Hence, it was termed as the limiting reactant or the limiting reagent. You can just make a conclusion just down there to say that therefore nitric acid is the limiting reagent. So using the mole method, this is how you can define, or this is how you can determine your limiting reagent. I hope this video has been very much helpful. Thank you.